things that you need to know about the image intensifier. And these 3 things have to do with how the image intensifier works in terms of the fact that it greatly increases the brightness. So the things that we're going to talk about will hopefully give you a good idea as to really the importance of this image intensifier compared to the early days of fluoroscopy. So 3 terms that you need to know. The first one is what is called brightness gain. And brightness gain has to do with the extent that the image intensifier will increase the image brightness. And not all image intensifiers are the same. Okay? So there are some differences. Some can increase image brightness more so than others. And that's fine because it just depends upon where the particular unit is going to be used. So that's what brightness gain is. It's how much it illuminates the image or increases the brightness. Flux gain looks at the number of light photons at the output phosphor versus the number of X-rays that entered at the input phosphor. So we're looking at the light that exits the output versus the X-rays that came in to the input. Okay? And like I mentioned to you, the fact that we've got 25,000 to 35,000 volts means those electrons are accelerated very rapidly to that output phosphor. And that lends itself to an increase in the number of interactions that those electrons undergo. So flux gain is looking at light photons versus the X-ray photons, the number. And then minification gain also plays a role in brightness because it increases brightness given the fact that the image size has been reduced. So we have an increase in image brightness simply because the size of the image has been reduced. So basically, it's like concentrating that image onto a smaller area. The output phosphor is quite a bit larger. The input phosphor is quite a bit larger than the output phosphor. So that lends itself to that beam or the electrons being concentrated into a smaller area. So when the light photons are produced, the image is brighter. Because you're taking something, an image that is spread out and narrowing it down, condensing it, that makes it brighter. So it will make the image brighter. So all of these have formulas associated with them. Brightness gain is flux gain times minification gain. Here's flux gain, it's the output light photons divided by the input X-ray photons, and here's minification gain. It's the input phosphor diameter divided by the output phosphor diameter, and it happens to be squared. Okay, so these are the formulas that manufacturers will use to determine these characteristics, and these are the types of things that would be included on their data sheets. If you're a manager and you have to purchase a new piece of fluoro equipment, this type of information would be available to you. Okay, so here's our image intensifier. Here's that curved portion. So at the curved portion, what end is this? Is this the output end or is this the input end? What's that end going to be? That's the input, okay? That's the input. And then I turned it on its side just so you can kind of see what it looks like from the side profile. And then here you're looking at the underside. So you see this area here is a lot smaller than the curved area here. This is the output end. So input end, output end, right? And it's quite a bit smaller. So let's look at these principles. Let's look at brightness gain and look at flux gain and minification gain. So you have an idea as to the impact that this intensifier has. So in this simplified example, and here I didn't draw in, the housing, the glass envelope here, okay, just to kind of save some space. But here we have one X-ray photon entering the input phosphor. Remember, the input phosphor takes the X-rays and converts it to light. So 1 light photon is greatly intensified to 10 light photons. And then there's not a gap here between the input phosphor and photocathode. I just did it for point of illustration so you could see these photons. That photocathode is directly against that input phosphor. But that photocathode will take these light photons and convert them into electrons. And in this example, it happened to convert 10 light photons into 30 photoelectrons. And then they're rapidly accelerated to the output phosphor. The output phosphor will take those electrons and convert them to 80 light photons. So we started out with 1 X-ray, but we have 80 light photons. Okay? So the flux gain would be 80. So how did I come up with a flux gain of 80? How do you come up with that? What's the flux gain looking at?
Oh, 80 divided by 1.
It's 80 divided by 1. So it's just simply looking at what we end with versus what we began with. Okay. So that's how a flux gain of 80 was calculated. 80 light photons divided by 1 X-ray photon gave a flux gain of 80. The important thing for you all to know about flux gain is that it's looking at the number of light photons at the output phosphor versus the number of X-rays. Okay, you're not going to have to calculate that formula, but you need to know that flux gain is looking at what we end with versus what we started with. Okay, so light versus the X-rays. You okay with that? But you won't have to work a problem. This is minification gain. So here in this example, the input phosphor is 9 inches and our output phosphor is 1 inch. So how did I end up with a brightness gain of 6,480? Actually, I should start with this, minification, because I said minification. How did I end up with a minification gain of 81? What is minification comparing? What is it looking at?
Diameter?
It's looking at the diameter of the input and the output. So the way this is calculated is 9 squared divided by 1 squared. Well, 9 squared is 81. 1 squared is 1. 81 divided by 1 is 81. So what you need to know about minification gain is it takes into account the size of the input phosphor versus the size of the output phosphor. Okay. And so it gave us a minification gain of 81. So then the way you come up with the brightness gain is equal to the flux gain multiplied by minification gain. So flux gain multiplied by minification gain. Our flux gain was 80. The minification gain was 81. So the brightness gain ends up being 6,480. It's just multiplied together. So the brightness gain gives the overall picture of the intensification properties of that intensifier. The typical brightness gains, and this will vary a little bit according to what source you read, but the typical brightness gain range for image intensifiers is somewhere in the neighborhood of 5,000 to 30,000. So if you have an image intensifier that has a brightness gain of 30,000, the image will have more brightness than an image intensifier that has a brightness gain of 5,000. But it doesn't mean that this is terrible or it wouldn't be manufactured like that. It all depends upon where it's being used. The purpose is for the image intensifier. Okay. So it takes the minification gain as well as the flux gain to give us the total picture of the illumination capabilities of that image intensifier, and that's expressed as brightness gained. So on a test, you may be asked, What does minification gain take into account? It's the size of the output and input phosphor. You may be asked, what does flux gain take into account? It's the number of light photons that we ended with versus the number of X-rays. And then brightness gain is the total picture of the luminance, because that brightness gain is the minification and the flux gain together. Okay, so you okay with that? But you won't have to calculate anything. You won't have to calculate it. So that's good. No calculations. So thumbs up, right? So I wanted to show you the formulas because your book also has the formulas too. But you don't need to memorize the formulas, but you just need to know what the comparison is between. Okay? Whether it's the size of the input and output or the number of X-rays versus number of light photons. Okay. Something else I want to show you is this thing called a conversion factor. Most of the newer units, instead of reporting brightness gain, are reporting something that is referred to as a conversion factor, and you'll see it abbreviated as GX. Okay, as GX. GX. What this is looking at is it's looking at the output phosphor illumination. So you can measure, when I say you, the vendors can measure the amount of light that is put out by that output phosphor. And remember, illumination or that light is measured in candelas. That's what the CD stands for. So it's candelas per meter squared. That's what brightness is measured in. So there are devices, photometers, that can be used to measure the light intensity that comes out of the output phosphor. And then they can take measurements of the input exposure. You know how we use the dosimeter to measure the tube output? They can do the same thing. They can measure the tube output, what's coming out of the X-ray tube, and what's going into the input phosphor. And if they divide the amount of light by the amount of X-rays, they come up with this thing that's called the GX factor, which is analogous to the brightness gain. It's analogous to the brightness gain. But this is just an easier way for vendors to report the luminance of their fluoro tubes. So to kind of give you an idea, when vendors report this GX value, this is how it would look. For example, 50 to 300. Another way to look at it is it's about 1% of the brightness gain value. So on the previous slide here, I told you brightness gain is around 5,000 to 30,000. 50 to 300 is 1%. So numerically, the numbers, it'll appear like this instead of in the thousands like you see here. And it's just because the way they measure it is different, but it's the same thing. So in other words, if one vendor reports a GX of 300 and another vendor reports a brightness gain of 30,000, those tubes are the same. Those image intensifiers are the same. It's just a different way of reporting it. Okay. So just, wanted you to be familiar with that. So for the GX, what you need to know is know that the GX looks at the light being emitted versus the exposure coming into it. The light being emitted versus the exposure coming into it. You're not going to have to calculate anything, but that's all it is. It's the amount of illumination. So it's the amount of illumination versus the input exposure rate, how many X-rays per second. So it's the light versus exposure rate. Okay. And it's 1% of the brightness gain value. 1% of the brightness gain value. As these tubes age, illumination is going to decrease. Okay, illumination decreases. Eventually, the image will be so dull, it has to be replaced. They have to replace it. Because what happens is as the tube dulls, as the illumination dulls, the exposure rate is going to have to increase to maintain that brightness. It's kind of like as our X-ray tubes age, we end up having to increase our mass to compensate for that. The same thing happens with image intensifiers. As they age, the exposure ends up having to increase, and it just gets to a point where that's just too much exposure to the patient, so the system has to be replaced. All right. So you okay with those intensification principles, brightness gain, flux gain, minification gain? Okay. All right. Something else you need to know about is with our image intensifiers, they may be referred to as multi-field image intensifiers because they have magnification capabilities. They have magnification modes. The typical spatial resolution for image intensifiers is around 3 to 5 line pairs per millimeter when we're using the largest field of view. You'll see this in a minute. We'll talk about this field of view. Okay, so the resolution with the largest field of view is around 3 to 5 line pairs per millimeter. So, that's sufficient to see large structures, but if you really want to see more detail, then we need a little better spatial resolution. So what you can do is, or what the radiologist would do, is at the push of a button, they would be able to put this image intensifier into magnification mode so that the spatial resolution will be better. Okay, it's not the same as, we talked about with spatial resolution that when you increase magnification, spatial resolution gets worse. This is a little different. So when we talk about magnification with fluoro, we actually get better spatial resolution. So it's not like magnification that we talked about when we did the section dealing with spatial resolution. Like if you increase the OID, spatial resolution goes down because you've got magnification. This is different, okay? This is a little different. So you just kind of have to get that straight in your brain. So with fluoro, when you're in mag mode, the spatial resolution actually gets better, okay? So this is an example of a multi-field image intensifier. You may have an image intensifier that has 3 different fields of view, 30 centimeters, 15 centimeters, and 10 centimeters. So what the field of view means is it's the size of the input phosphor. So you can actually change the size of the input phosphor that is being used. You can change the size at the push of a button, okay? As an example, if you go from a 30 centimeter to a 15 centimeter, the 30 centimeter is the largest field of view, down to a 15 centimeter, what happens is that a smaller area of the input phosphor is going to be utilized. So a smaller area of the input phosphor is going to be utilized. What else happens is the system will increase the voltage to those electrostatic lenses. So there's going to be higher voltage going to those lenses. And since there's higher voltage going to those lenses, the electron stream will decrease its diameter even more. So it really does narrow that beam, those electrons. The focal point will shift further from the output phosphor. Here's where the focal point, because I kind of showed you the general area of where the focal point was when we looked at that graph that I had with all the components, but here's where you'll see it. Here's where you'll actually see it a little better. So when that focal point shifts further from the output phosphor, the result is a smaller area on the output phosphor is going to be hit by the electrons, and it makes the image appear larger. So this is what we mean by magnification. So the image will appear larger because a smaller area of the output phosphor is being hit. Okay. So this is kind of what it looks like. So here we've got that curvature I was telling you about. So if we use the entire diameter of this input phosphor, for our example, this would be like the 30 centimeters. So we're using the entire diameter. You can see this represents the electron beam. This is the focal point. What happens is the electrons get focused to almost like a single point, but then they end up diverging out to hit the output phosphor. Because again, we don't want the electrons to be just a single point. The electrons have to verge out to give us the image. Otherwise, it would just look like we've got a single point for the image. So this is what it looks like if we're using the largest field of view, that 30 centimeters. If we change to 15 centimeters, it restricts the size of the input phosphor. So it restricts the size, it narrows it down. So this is like, 15 centimeters. So it narrows it down. It narrows the size of that input phosphor down. Notice what happens to the focal point. Since the beam is narrow because of a smaller input area and because of the increased voltage to the lenses, we get a lot narrower beam than what we have with the 30 centimeter input phosphor. So that focal spot has shifted. See, it's shifted further back. It's a little further away from the output phosphor. So then what happens is when these electrons do diverge out, what happens is they actually end up hitting a smaller area because the beam is so narrow. It hits a smaller area here, but because this focal point is a little further away, it magnifies the image. Kind of like when you increase the OID, it magnifies a part. Remember when we increased the OID, we used like a 10-inch sponge for whatever we were doing, hand or elbow, and it magnified the part. Since this focal spot's further away, the part is magnified, but with fluoro units, it does not result in a decrease in spatial resolution. The part, essentially what happens is, even though it's called magnification, it's more like you are zooming in on the structure. So it's more like you are zooming in. It's called magnification because this focal spot is further away from the output phosphor. But in reality, it's more like you are zooming in. Kind of like when you look at an image on the workstation and you hit the little zoom button to focus in or magnify a structure. That's what's going on here. Okay, so it's referred to as magnification, but it's more like you're zooming into a smaller area of the structure, and that allows you to have better spatial resolution. Okay. So the result is it is a magnified image. It'll appear larger, but yet it's more like a zooming in feature. It's not magnified in that you are losing spatial resolution. It's just a closer view of it. You get a closer view of that image. So it's like you're zooming in on it. So the advantage to that is increased spatial resolution. Since you're able to zoom in on that image and see it closer, we have an increase in spatial resolution. So that increase in spatial resolution, it's because of that smaller input phosphor area. So in other words, the beam doesn't diverge out as far because it's taking up a smaller area on that output phosphor. So that's why that spatial resolution is increased. The more a beam diverges, the less spatial resolution you have. So we have better spatial resolution because the beam did not diverge out. Okay, it didn't spread out. So we have better spatial resolution for that area that we're looking at. Now the downside though is that patient exposure is increased. And it has to do because of decreased magnification gain and brightness gain. So what that means is, if this is the only area that is activated on the input phosphor, we are losing all of the x-rays on the periphery. We're losing that exposure. And so if we're losing all of that exposure, the image is going to be dull. It's not going to be bright because we have lost all of these electrons around the periphery here. We have lost that. So what the system has to do is it has to increase the exposure to account for losing exposure on the periphery here. We need to maintain the image brightness. So the downside to magnification mode is that patient exposure will increase. Patient exposure increases to have enough brightness. And you have to think about, makes sense, because if we have a smaller area of that output phosphor being hit, we're not going to have as many light photons being produced. So therefore, the exposure has to increase to give us that brightness back. So the plus side of mag mode is better spatial resolution when the radiologist needs to see some better sharpness. But the downside is patient exposure is going to end up increasing. So the radiologist should only use the mag mode when they truly need to see better image detail. Okay, because they need to minimize patient exposure. All right, you okay with that? You think? A little bit? It'll take some digesting. All right. So that's the image intensifier. Okay? That's this component here. That's the image intensifier. Now what we need to take a look at is something that is referred to as a video camera. Okay? Video camera. This is a video camera here. The video camera is known by some other names, and sometimes this can get confusing. This is something that you just have to kind of memorize so that you don't get confused with this. The video camera is also referred to as a television camera or a camera tube. Television camera or camera tube. Now, when I say television camera, I am not talking about the television monitor where you view the image. It's not the television monitor. It's called a television camera. Okay, television camera. So the video camera is this device here that is in between the image intensifier and the television monitor. Okay, so this is the video camera, the television camera, or the camera tube. So what happens is light that leaves that output phosphor, it's going to travel through either lenses or fiber optics, because that light, we don't want to lose the light. That light is our image. So that light needs to be directed either through fiber optics or lenses to the video camera. Okay, that's the only way light can get into that video camera is by either lenses or fiber optics. So that light from that output phosphor will be directed to this thing here that's referred to as a video camera. What this video camera does is it will take that light and it will convert it into electrons. So it converts it into the electronic signal or a video signal. Okay. So the image intensifier releases light, and then that video camera will take that light and it will convert it into electrons. So our image data is now back in the form of electrons. Okay. So we're now into the form of electrons. And then the TV monitor here, what it'll do is you know, it'll end up taking those electrons and displaying it as an image. Okay, but this video camera will take that light and convert it into electrons. There are two types of video cameras. The original video camera was referred to as a Vidicon. Okay, it was a Vidicon. We'll take a quick look at that in a moment. Newer units have a camera that is a CCD. Okay, so CCDs are not only used as an image detector, CCDs are used in fluoro units. They're used in fluoro units as well. Okay. So this is what a Vidicon looked like. It's a vacuum tube. So it would connect it would have either lenses or fiber optics connected to it, and that light would come in, and this particular tube here, the Vidicon, this vacuum tube, would take that light and convert it into electrons and then send it to the television monitor to be displayed. Newer units have a CCD. Our unit downstairs, even though our fluoro unit is an older unit, you know, it was manufactured back in the 1990s, it has a CCD. So the light from that output phosphor will be sent through either lenses or fiber optics to that CCD. And when the light hits that CCD, the CCD will convert it to electrons. Okay? The CCD will last a lot longer than this vacuum tube. So that's why newer units will have CCDs in them. Okay? All right. Let me see. Okay. All right. So, you know, how do we end up with these images? If the fluoroscopy unit has a CCD video camera, what takes place is the electrons that are generated in the CCD will stream through an analog to digital converter, and this analog to digital converter is located in between that CCD video camera and the display monitor. All right. So what in the world is meant by that? Have any idea? Probably not. Why are the sirens going off here? Oh, shoot. Okay. Hey, look, guys, we have an armed and dangerous person on or near campus. Okay. So we are going to stop here. Okay. You will be getting the alert, Carolina. All right.
Okay.
Okay. Stay safe. And when I post Monday, November 9th, by 8 a.m., I will have that assignment posted, but it'll be due, like I said, probably around 8 p.m., okay? All right, do y'all have any questions? All right, y'all stay safe.
You be safe.
Thank you.
Yeah.
Really? Okay. Oh, Jesus.